The final step is to relate what's called the absorption coefficient, often written as alpha, and that's the probability of absorption of a photon per unit length, to the total transition rate per unit volume we've just calculated. Incidentally, when we talk about absorption coefficient being the probability of absorption of a photon per unit length, it's really best to think of that as if we had a very thin sheet of some very small thickness, delta Z or something, and we're looking at the probability of a photon being absorbed in a very thin sheet, and that would be alpha times the delta Z. We're not really thinking we're working with a unit length of material. So this absorption coefficient is the absorption per unit length, the probability of absorbing a photon per unit length. So a thin sheet would have an absorption probability of alpha times the thickness of the sheet. With some photon energy h bar omega, the number of photons incident per unit area per second is by definition the intensity, that's the amount of energy per unit time per unit area, divided by the energy of a given photon. So that's the number of photons that arrive per unit area per second. And I here, as we said, is the optical intensity, that's power per unit area. So the probability a photon is absorbed per unit length, again thinking that we're only working with thin sheets, is this ratio of the total transition rate divided by the number of photons that are arriving per unit area per second. So the total transition rate per unit volume, number of photons arriving per unit area per second, and we can rewrite that using this simple relation here to get h bar omega times the total transition rate per unit volume divided by the power per unit area. Now, from electromagnetism, we can deduce the intensity from the known vector potential amplitude, and the formula for that is as I'm showing here. And in this formula, nr is the refractive index of the material, c is the velocity of light, and epsilon naught is what used to be called the permittivity of free space, though it's now more correctly called the electric constant. Anyway, this is just a formula, and as I said before, the intensity is related to the square of the amplitude of the magnetic vector potential that is oscillating in this electromagnetic field. Hence, with this expression we've just written down for the absorption coefficient at some photon energy h bar omega, our whole expression becomes the following. Everything here was our expression for the total transition rate per unit volume. This expression here is h bar omega divided by that formula for the intensity. So now with the amplitude squared of the magnetic vector potential down in the bottom line. And we can cancel a good number of things here, including the intensity, and the resulting expression we get is what we have here. This PCV squared is sometimes more conveniently written in this form. PCV squared is a quantity that comes up in band structure calculations as well, and solid-state physicists or semiconductor physicists have preferred to express this in terms of an energy, and this energy parameter, which just involves 2 divided by the mass of an ordinary free electron, is approximately the same in a broad range of materials. It's approximately equivalent to about 20 electron volts. As a result, we can use this particular formula actually to calculate a first model for optical absorption in a large number of different semiconductors. So using this EP parameter as the more conventional unit that we typically have for expressing PCV squared, this is our formula then for the optical absorption coefficient in a semiconductor in this model. In direct gap semiconductors, this optical absorption model gives us an absorption that rises as the square root of the photon energy's excess energy above the bandgap energy. So in this model, here's what the absorption coefficient would look like. We could think of this as the amount of absorption, relatively speaking, in a thin sheet of material. So up to the bandgap energy, there's essentially no optical absorption, and then when we hit the bandgap energy with the photon energy, the optical absorption rises according to this curve here in this model. And this model is used as the starting point for optical calculations in semiconductors. We often add other things to it. There are some other important effects we do need to consider, but this is the starting point for many of our models.